Today I have the pleasure to introduce Professor Mostafa Elseifi. Professor Elseifi is the Occidental Chemical Corporation Distinguished Professor at Louisiana State University in the Department of Civil and Environmental Engineering. He earned his bachelor's from Cairo University in Egypt, and then his master's and doctoral degrees from Virginia Tech, all in civil engineering. His research interests include infrastructure resilience, sustainability, asphalt materials, machine learning, and pavement evaluation and management. So I guess this is the perfect audience for you, Professor Elseifi. Please, everyone, join me in welcoming Professor Elseifi. Go ahead.
Okay. All right, good afternoon, everyone. Thank you for joining us. I used to work at the University of Illinois, so I know the place very well. Actually, my advisor was Professor Al-Qadi, so it's a continuation of different generation, I guess. All right, so I'd like to acknowledge my graduate student, Hussam Abu Hamir. He did most of the work here. I just helped directing him and giving some idea. So if we start with an introduction, you probably have heard about OGFC. It's a very popular type of mix, especially in particular part of the world. For example, the Netherlands, Japan, and some states in the United States are frequent user of OGFC. So it provides many advantages. Is that it serves like a reservoir where it can store the rainwater and then drain it to the side or underneath the road. It also provides significant reduction in noise. Especially during wet weather, it improves the friction characteristic of the pavement, and it also reduces the risk of hydroplaning for the driver. However, some of the problems that are quite significant is that the performance of OGFC is significantly inferior to dense graded mix. And also many practitioners will tell you that the functionality of OGFC gets reduced significantly over time. So it starts very good, but then the air voids start to be clogged, and you basically lose the benefit, and you are still stuck with poor durability. So here are some examples of the benefit. You can see the reduced hydroplaning between two different mixes. You can see the reduction in accident rate, especially during rain event. So you can see here the significant difference between a dense graded and the OGFC shown in green. However, some of the deterioration, raveling is a major issue. You see it everywhere where OGFC is used. Also, the literature reports early top-down cracking with this type of mix. Especially, it's a very thin layer, so you get significant early top-down cracking in this layer. The reduction in noise, you can see here in a study that was done in Nevada, there is significant reduction in noise, and that can really help, especially in urban setting. However, the cost is quite high. So you can see here the cost of OGFC as compared to dense graded, it is more expensive. And one of the reasons is that the asphalt content is higher than with dense graded, and we have to use some types of modification, either polymer or any other type of modification to try to enhance the performance. The construction issue are well documented. As I said, it is a thin layer, so the compaction can be quite tricky. And this study was done in NCAT. You can see the reduction in permeability over time. So that was done at the test track. You can see the the permeability starts high, and then due to the action of traffic and the settling of the void, you can see there is a reduction in permeability. So our objective were twofold. First, we wanted to evaluate different type of additives and technologies that can help enhance the permeability of OGFC while maintaining its functionality. And the second objective was to investigate the seepage behavior of pavement structures that have an OGFC using finite element analysis. This is a general research approach. So we started with the literature reviews, and we worked on the literature. We also came up with some new idea on what to try. And then we evaluate the performance, and we developed the finite element model to study the seepage analysis. And I'm going to, based on the result of the finite element, we developed a tool that can predict the seepage behavior of OGFC layer. And then based on these results, we provided some recommendation on how to improve the performance of OGFC layer. So if we start with the experimental program, this is the Factorial. So CM, you can see it here, this is a control mix. So this is a plant mix. So we got it from the contractor. So it has been approved, and it meets all the specification. And after that, what we did is that we started playing with this mix a little bit. So the first three mixes that you see here are warm mix OGFC. So the first two use a chemical additive. The next one use an organic additive to achieve warm mix. After that, the first mix shown in purple is chrome rubber OGFC. And then the next mix that you can see here is chrome rubber OGFC, but because chrome rubber, as you can see at the bottom, would cause an increase in mixing temperature and compaction temperature, we combined chrome rubber with warm mix asphalt additive. And you can see we managed to reduce the temperature to what was the control mix was used. The last two are kind of new type of mix. The first one, we decided to replace all the passing 200 with Portland cement. And the last one, we replaced all the passing 200 with fly ash. So the idea is try to improve the adhesion of the mix and try to enhance its durability. The Factorial was quite comprehensive. So everything was done at the Louisiana Transportation Research Center. So it's a very nice laboratory, and it's AASHTO certified. And again, we managed to do a large suite of laboratory tests to assess different characteristics of the mix. So we started by measuring the air void, and you will see throughout the presentation we have two main criteria. The first one is based on the Louisiana criteria, and sometimes the Louisiana criteria is either different than the NCHRP 155. So we added another assessment, which is the NCHRP 155. So air void content for Louisiana has to range between 18 to 24. NCHRP requires that the minimum is 15%. Then we measured the permeability coefficient, which is not required in Louisiana, but we have it in the NCHRP. We assess the drain down with the maximum is 0.3%. To assess the compaction phase, we measure the compaction energy index, which is based on the compaction curves that you obtain from the gyratory. Basically, it measures the area under the gyration curve and assess the lower this area, the more energy efficient your compaction is. In terms of performance, so we conducted the Contabro abrasion test, which again if you look at the literature, is highly recommended for OGFC layer or mix. We also assess the rotting performance using the Hamburg wheel tracking test. We assess the cracking resistance using the Texas overlay test. Then we assess the stripping resistance using the modified Lotman test and using the boiling test. So currently, Louisiana requires a boiling test for OGFC, but doesn't require the modified Lotman. And this is one of the recommendations is to consider the tensile strengths that we obtain from the modified Lotman test as one of the criteria that can identify good performer from bad performer mix. If we move to the results, so I'll try to go quite fast because I want to present quite a lot in a small amount of time, but hopefully I will be successful. So with respect to the air void, you can see that when we use a warm mix as an additive, which is number 2, 3, and 4, there is a reduction in air void. And again, the reason is that the warm mix additive act like a lubricator. It reduces the viscosity of the binder, and that's again reduce the air void a little bit. However, it's still within the spec, so that's good news, I guess, in this way. The other mix also performed comparably, so they all met the requirement. So that was a positive sign. We also looked at the permeability. So this is the minimum requirement set by NCHRP. So you can see again, the warm mix asphalt additive reduced the permeability. The chrome rubber also reduced the permeability. And the reason it reduced the permeability is that when you add chrome rubber, it kind of swell. So it reduced it increased the volume that the binder is occupying, and that's why you get this reduction in air void. The last two mixes were very similar to the control mix in terms of permeability. All right. If we go to the drain down, so the drain down test was performed, and the maximum is 0.3%. And you can see that all the mix met the drain down. We used fiber in this mix. So again, that's even the control mix had fiber. And that's a very successful methodology to reduce drain down issue with OGFC. In respect to the compaction energy index, you can see that as expected, the warm mix asphalt additive reduced the compaction effort needed to achieve the density requirement. And again, that was expected. And even though we reduced the temperature by 25 degrees Fahrenheit, but that's the good thing about warm mix is that you reduce the temperature and at the same time you reduce the compaction effort. So that's, again, that was a very positive sign. And again, we changed the requirement a little bit because the air void requirement is different for OGFC. So the compaction energy index was measured until 75% gyration, which is different than what we use for dance group. With respect to the contemporary loss test result, as I said, this test is highly recommended. It's not currently required in Louisiana, but we think that this should be added to the spec. It's basically, it's like a torture test. You put this sample into the Contabro, into the Los Angeles abrasion drum. Then you rotate it and you measure the loss in the mix weight. And we did this test at 3 settings on age. The maximum requirement by NCHRP is 20%. And we did it for age and moisture conditions. So these are the results. You can see that they all met the Contabro test, even though we had some variability. And you can see the best performer here are, so we have these letters here, which are the statistical assessment of the mix. So the control mix is like a B. The best mix was chemical additive 2. And statistically, all of this are can be classified as A. So that's why they all met the 20% requirement. And this is set by NCHRP. As I said, my vision with this test is that we need to be able to differentiate the good performer from the bad performer. So if they all meet the requirements, so that's maybe means that the requirement is maybe a little too loose. But that's again something that has to be validated in the field. With respect to the age and the conditions, they all met except the control mix. Control mix failed the conditioned and the age criteria set by NCHRP. If we move to the rotting test, so that was done based on the Hamburg test. And we have two requirements. One of them is set by Louisiana, which is the rot depth at 5,000 passes. And you can see that they all met this requirement, even though the organic WMA was the best performer, as identified by the letter A. And it was followed by the chrome rubber OGFC, the mix with the cement, and the mix with fly ash. If we look at the NCHRP requirement, which is at 20,000 passes, so this one is a little bit more rigorous, you can see that a number of mix failed this requirement: the control mix, chemical additive 2, and the chrome rubber OGFC. The best performer again was the organic WMA, and you can see that these three also passed the 20,000 passes requirement. The Texas overlay tester, we have two requirements. We have the crack initiation requirement, and it has to be between 1 and 3, the amount of energy to initiate the crack. So they all met this requirement except chemical 1 OGFC. The crack propagation rate requirement is set at 0.5, and again, they all met this requirement, with chemical 2 OGFC being a good performance, and the control mix also was a good performance. So they all pretty much were the same in terms of the Texas overlay test. With the modified Lotman, the TSR set by NCHRP is 0.7, and again, we had an anti-stripping additive in this mix, even the control mix, and that's again, keep in mind that in Louisiana we get like 65 inches of rain per year, so it rains pretty much every week around the year here. So we have to use anti-stripping to make sure that we don't get stripping damage, even though we still get stripping damage, but it helps reducing it in the mix. With respect to the boiling test is a qualitative test, and it is required by Louisiana DOT for OGFC. So we couldn't find any stripping sign in any of the mix that we tested. So if we summarize the performance evaluation, so the red cell means that they failed, and you can see that we have 4 mix that met all the requirements. The organic OGFC, which has an organic additive warm mix, the chrome rubber OGFC, the cement OGFC, and the fly ash OGFC. So again, these 4 mix are, in my opinion, are highly promising, and we think that the next step, and again, keep in mind, this control mix is placed in the field. So again, you can see by the red that it has some durability issue as identified by the laboratory testing program. And that's again, we have some durability issue with OGFC, and that's why we are trying to improve this. So we think that a field evaluation of these 4 mix will really help move this research forward in terms of implementing the results. So the finite element modeling, so it was a seepage analysis. So I'm going to start by the calibration and the validation of the model. So what we did is that we did some coring and some GPR testing in a field site. And we used this measurement to calibrate our model. So that's, again, we had to do some assumption during the modeling phase. So we use these results to validate and to calibrate our model. So the finite element analysis, we did a steady state analysis, then followed by the transient analysis. The steady state analysis allowed us to fine tune the initial condition. Then the transient analysis basically consists of applying a water flux or a rain on the pavement, and then our output is the time it takes to reach saturation. So you have to think of OGFC as a water reservoir, and if this time, the longer this time to reach saturation, the better the OGFC is. So these are the material properties. So as I said, some of them were measured based on the cores that we extracted, and some of them were assumed. And after that, as I said, we calibrate our model. This is the layout of the model. So it's a three-dimensional model. And again, it's used to do slippage analysis. So we apply the water flux, and then we looked at the water flow and the time it takes to reach saturation. And this criteria shown here are based on the field measurements that we conducted. For the steady state analysis, again, all of these are based on the initial conditions. So we measured the amount of water that we had during the GPR survey. And during the transient analysis, we applied the water flux that you can see here. And we simulated different rain intensity that can be applied on the OGFC layer. For calibration of the model, so we collected cores and GPR survey. You can see it here, the trace, and we use this equation, which I'm sure you're all familiar with, to calculate the dielectric constant of the base layer. So we have the time for propagation, and we have the distance from the core, so we can calculate the dielectric constant. And after that, after we measured the dielectric constant, we use Top's equation to calculate the volumetric moisture content, which was, for this particular case, 0.3. And the model predicted the moisture content, so you can see it is not quite equal. So this allowed us to change the model parameters a little bit until we got an acceptable fitting. And another thing that we added to the model is that we noticed that there is a very strong reflection underneath the pavement, and we assume based on the literature that this is a groundwater table. And it's at 0.6 meter, which, as I said, in Louisiana, we get so much rain that this is not uncommon for us. So we changed the model parameters, as you can see here, and then we calculated the volumetric moisture content in the base until we got a comparison between 0.3 and 0.31. So we assume that the model is properly calibrated. Then we use this model to do a parametric study. So we change the permeability coefficient and the thickness of the OGFC layer, the rain intensity, the permeability of the existing HMA. And then one of the first things that was done here is that we simulated the amount of traffic. And to simulate the traffic, actually, we didn't have a wheel. So what we did is that since it is shown in the literature that there is a reduction in permeability over time, based on the slides that I showed you from NCAT. So we simulated different traffic conditions to simulate the wear that happens to the OGFC layer to see how it affects its effectiveness. So the output of the model, as I said, is time to reach overflow condition, meaning the time to reach complete saturation of the OGFC layer. So think of the OGFC as a water reservoir. And again, even though you get some infiltration, but if you have an existing asphalt layer underneath it, the infiltration is not as much. But also in Louisiana, because the weather is so hot, we also get evaporation. and we did simulate the evaporation process in the model. So we first, by identifying the critical location, so we looked at the left wheel pass and the right wheel pass, so you can see it here. And you can see that the right wheel pass is more significant because the time to reach saturation is shorter than for the left wheel pass. With respect to the OGF thickness, it made quite a bit of a difference, as you can see from these results here. So obviously, the greater the thickness, the more storage or the more drainage capacity you have. And you can see by the red line that shows the maximum thickness that we looked at, which is 1.9 inch. We also looked at the effect of the OGFC permeability, and interestingly, it didn't make a big difference. So that's something that, again, it will show in the statistical analysis that I will show you. The existing permeability made quite a bit of a difference, as you can see here. And again, this controls the amount of infiltration that you get to the underlying pavement. The rain intensity was also a very significant factor. So again, the higher the rain intensity, you can see here at 0.1 inch per hour, the faster it will get to saturation for the OGFC layer. And that's again an example of flooding condition when you get such a high rain intensity in a short period of time. The traffic wear made a big difference at the beginning. You can see it here. And after that, it did make a difference, but it was not as significant as the beginning of our assessment. So we did a statistical analysis to assess which factors are more significant. And you can see that they were all significant except the permeability coefficient of the OGFC layer. And again, that was something I was pointing out previously. So what we did after that is that we developed a model to determine the time to reach overflow. And again, this model, you will see that we'll use it in something very beneficial. So we developed an ANN model, which again is something that provides us with very high flexibility for, reach a level of very good accuracy, much better than, for example, using multilinear regression or something of this sort. So the model was, as expected, with ANN model, you can reach a very good accuracy. You can see here the R square was quite high. The root mean square error was less than it was 5%. You can see it here. And this is the fitting stage. Then we repeated the same using output from the finite element models that were not used in the validation. And we also had a very good accuracy. Again, we did a statistical comparison between TC predicted from the model and TC obtained from the ANN, and they were statistically equivalent, which again, what we want. So what we did with this model is that we tried to look at the air void effect on the time to reach overflow saturation. And the reason for this is that Louisiana currently requires 18 to 24%. So we wanted to know what is the minimum air voids that we can use that will provide us with acceptable effectiveness in terms of time to reach overflow saturation. And at the same time, would be relatively lower air void contents, which doesn't affect the durability as much. So we identified the optimum air void content. So again, you can see here you want your degree of saturation not to reach 100%, because if you reach 100%, that means that your water will start accumulating at the surface. So the minimum air void that will allow us to keep the degree of saturation not as much and over the service life of the pavement was 14%. And that's for a continuous rain of 0.5 hours. So I'm sure that we have some folks from Louisiana, so they will tell you, well, sometimes it rains more than this. So we did the same analysis, but for 1 hour continuous rain. And you can see the minimum air void content that will keep the saturation level less than 100% is 16%. So that means that we can use an OGFC of 16%, and that's again over the entire service life of the layer, and we'll still not reach overflow condition at 1 hour of continuous rain. So in conclusion, we first that the WMA additive and the chrome rubber reduce the air void content and coefficient of permeability. And as we said, for the WMA additive is because of this lubrication action of the additive. For chrome rubber is because of the swelling. We found that WMA additive, chrome rubber, Portland cement, and fly ash all improve the raveling resistance as compared to the control mix. All of the mix met the rotting requirement at 5,000 pas. However, at 20,000 pas, only the mix that contain organic WMA, chrome rubber, Portland cement, and fly ash satisfied the permanent deformation requirement. We found that actually the Portland cement was the best performer in terms of the Texas overlay tester. It improved the crack initiation resistance by as much as 70%. So it's a very promising mix. In terms of the ITS dry and wet test results, again, the WMA, the chrome rubber, the Portland cement, and the fly ash all improve the cracking resistance in terms of the indirect tensile strength. In terms of the TSR and the Boyd test, they all predicted acceptable moisture damage resistance. And as I said, we had an anti-stripping additive. And in terms of compaction energy, we found that the WMA OGFC had a reduced compaction effort and also a lower compaction temperature. In terms of the finite element, we found that when we increase the thickness, the permeability, and the permeability coefficient of the underlying layers, they all increase the storage capacity of the OGFC mix. We also developed this ANN model, which was able to predict the time to reach overflow condition with a very good accuracy. In terms of recommendations, so again, this is still fresh, so we didn't get to the implementation phase. We still are doing some additional binder testing, and we are actually evaluating a couple of more mixes. In terms of our recommendation so far is that we think that we need to do a field evaluation of the organic WMA, the chrome rubber OGFC, the OGFC with cement, and the OGFC with fly ash. We also think that the requirement for the air void can be reduced from currently it's 18 to 24. We think that we can reduce it to 14 to 18, and that will really help with durability. We recommend to consider adding the rod depth requirement at 20,000 pas because it was able to identify some problem with the control mix and with other mix that we evaluated. And we also recommend added the Contabro test requirement for OGFC mix, and it's currently not considered as part of the spec for Louisiana. So acknowledgement, this study was funded by the Louisiana Transportation Research Center. So we thank them for that. We also received quite a bit of technical assistance from Paragon Technical Service, especially with the Contabro test. So far, as I said, these are fresh results, so they are not part of any final report. So they may change. I apologize for that, but you have to forgive me for that. All right, so that's all I have. Thank you so much for your attention.
Okay, so it's time for questions. Does anybody in the room have any questions for Professor Elseifi? Yes, Renan?
Hi, Professor. Thank you for the presentation. I was just wondering, the permeability of the asphalt mixture should change with the change in saturation. As the saturation increases, the permeability should decrease or increase. Was that considered in your seepage analysis?
You raise a good point. Like the permeability will decrease when you get intense rain. We did not consider this as part of this analysis, but that's something that, again, like because you have some mechanical effect and you have some seepage effect, so when we looked at the traffic wear, we reduced the permeability. So my guess is that if you want to consider the reduction in permeability, the reduction in due to traffic wear would be quite similar. So that's something that a very good point that we may consider in the future.
Any more questions? Okay. We have a question on Zoom from Mahdi. Mahdi, do you want to?
Hello, Professor. Thank you for your presentation. Can you hear me?
Yes, I can hear it.
And could you please explain more about Cantabro loss? Actually, I didn't understand. The result was lower from the first sample, or it was higher? And just a little more explain, please.
Sure. So for the Cantabro, you basically place your OGFC sample in this drum, and you start shaking them so they will impact and they will lose some mix, and then you measure the loss in the mix in the specimen weight. So it's a quite simple test. So we can do it in 3 phases. We can do it in unaged, and we can do it aged, and we can also do it moisture conditions. So we did the 3. So we found the requirement for NCHRP is 20% loss for the unaged, and it's 30% for the age and the conditions. So we found that for the unaged, they all met the requirement. However, when we looked at the condition and the age, we found that the control mix did not meet the requirement of the Cantabro test. And what does it mean? It's an indication of raveling resistance. This is the main distress that they link the Cantabro test to. And remember, in my introduction, I pointed out that raveling is one of the main factors that is causing early failure with OGFC.
We have another question from Deb Mishra.
Thank you, Mostafa. This is Deb Mishra from Oklahoma State. Excellent presentation. Thank you very much. Quick couple of questions. So what's the typical OGFC thickness in Louisiana? Because in your model, you went up to 1.9 inches. That's one. And the second one, I think I understand how you are incorporating your effect of traffic. You're basically just following that curve kind of to reduce permeability, but are you doing anything else to like in your seepage analysis to incorporate the level impact of traffic? Thank you.
Yes, so in terms of the seepage analysis, you are correct. It's based on the traffic wear. Is that we reduce the permeability, and that's if you take a look at I think the second or the third slide, at NCAD they tested the permeability at different traffic level, and they found that there is a significant reduction in permeability. What was your first question?
Typical thickness of OGFC in
Louisiana. So we have Sam Cooper here, so maybe he can correct me, but I think it's 1 inch. It doesn't or 1.5. That's the typical thickness that we use. That we use in Louisiana. Around the country, I think this is around the same. Yeah, someone was asking the same question on the chat, is what is the typical thickness of the OGFC layer? So it's between 3/4 to 1.5 inch thickness.
Okay, and last thing is, what software was used for the CPEG? Is it Abacus or something? What was it?
No, it's called the SEEP 3D.
Oh, okay. Thank you.
We have a question in the room from Egemen.
Thank you very much, Professor. Can you hear me?
Yes.
In the GPR, you use the two-way travel time. How did you make sure that the thickness wasn't changing when you were doing the GPR?
Oh, we conducted we got the GPR scan at very close to the core, and that's
Okay.
yeah, that's where we used it.
Okay. Okay. Thank you.
Sure.
There's also a question in the chat from Javier. He says, Professor, would you recommend using the Cantabro for SMA mixes with soft aggregates? Which condition?
So with SMA with soft aggregate, so it's mostly used with OGFC. So I would think with SMA, you probably can do, like, raveling may not be an issue with SMA. So I guess you may find some useful results, but as I said, is because you have to think about it, is that when we get the loss in mix weight, it's similar to raveling, because raveling is that you lose adhesion and then you lose some of your aggregate. So with SMA mix, I'm not sure that it will really give you something that will make sense anyway.
Professor, I have a question if nobody else has one. I had a question about the GPR part. You mentioned that you used Top's equation. And why did you use this equation? This equation is for soils. Why did you not choose an asphalt equation? It's calibrated for soils.
Oh, I may not have been clear, but we use it for the base aggregate. It was not for the asphalt.
Oh.
So, yeah, looking at the literature, it seems that there is a lot of acceptance in a way for this equation for aggregate and for soil. So that's why we used it.